in our optimization, many of the methods rely on the gradient of u of theta, and that's why we're going to be looking at a few different options for estimating that in this lecture. So because theta will generally be multiple variables, otherwise we'd have a very simple policy, gradient u of theta is going to have this form. So for every theta I, we're going to have a partial derivative. And let's say that we have n of these parameters theta. For the example that I just showed you, n would be 2, and this is going to give us an n by 1 vector. And before I go on, I wanted to make a note. This portion of the lecture, and also probably your portion too, is pretty calculus heavy, and depending on your background, you may have done that more or less recently. So I don't want you to feel like calculus-related questions are less legitimate than questions about material that maybe you've only seen in this course. I definitely had to look up stuff preparing for this, and if the calculus was a sticking point, please say something. We want you to feel good about every step that we're taking. So the first method is something that you probably saw in early calculus, and that's going to be finite differences. So in finite differences, we have some function and then some point where we're interested in computing the derivative. And does anyone remember what we do for this method? No worries. So we're going to take another point, some small distance away that we call delta, and we're going to compute the slope between those two. So the dotted line is the thing that we're computing, or the dotted line is the thing that we're estimating. The non-dotted line is the thing that we're computing. And we're using that to get a basic approximation just around that one point of interest. So in the multivariable case that we're considering for the gradient of u of theta, this is going to look something like u of theta plus delta E1 minus u of theta all over delta. And then we're going to do one of these for each of our parameters theta. So you might be wondering what this E here is. This is a standard basis vector, and this index indicates the position at which we have a 1. All other positions are going to be 0. So here we would have a 1, followed by n minus 1 zeros, and so on. And the reason that we're doing that is that we're only applying this difference delta to one parameter at a time. And so this is going to give us an n by 1 vector with a simple estimate of the gradient of u of theta around some point. Does anyone have questions here? How do we feel about the first one? Yes?
What's u again?
Great question. U is the utility of theta, and we get u of theta, as Josh mentioned previously, by using rollout simulations. So this is something that can impact this method, is that depending on the variance of u of theta, it may take a lot of rollouts to get a good estimate. And the book talks about some techniques that you could practically use to mitigate the potential invariance between when you're computing this and then running policy. Yes?
The theta here are the parameters for the parameterization. I guess like for eigenvector case, will this first order approximation always work?
Oh. So the question is, for the higher dimensional case where we have a lot of thetas, would this first order approximation always work? kind of depends on the data that you're working with. We will get into more complex methods that are a bit more robust, but you can imagine like if the theta parameters are on very different scales, then you may run into issues applying the same difference to all of them. So this would be ideal for a simpler case, and some of the other methods would be better for cases like what you're talking about. Okay, anything else? Cool. Okay, so the next method that we're going to talk about is called the regression gradient. And this may have come up in other ML classes that you've taken, but when we do a regression, we have some set of data points, and then we're finding the line that best fits them. So this is that regression, and what we're going to talk about is what the line is that we're fitting. So we know that the thing that we're interested in is that we want to find the gradient of u of theta. And around some point theta, we're estimating what this line would be. So the first thing that we're going to do is we're going to collect data points, and then we'll fit our regression line. So what should the data points be? We're interested in theta, and we want to collect a bunch of points, let's say. This is where theta is. And we want to collect points around it in its neighborhood, which we can find the gradient at. So we're going to create this matrix that we'll call delta theta. And we're doing a perturbation for each of our parameters. And this is going to be m by n, where m is the number of perturbations, and n, again, is the number of parameters. There's no right or wrong answer for choosing the number of perturbations to do. Empirically, a rule of thumb is to have double perturbations, double that number of parameters be the number of perturbations, but that could be based on computational constraints or expert knowledge, or you tried a few things and this is what worked the best. And then the way that you get the perturbations is also something, there's no one analytical option that's the best, but empirically we find that randomly sampling from the normal distribution works well, and these are also going to be normalized random samples. So you can visualize that as though we have a sphere and we're sampling points along the surface. And so those would be what the perturbations are. So that's how we get our changes in theta. Yes, question?
Just wondering, if you're randomly sampling around that point theta, how are you getting a line from that?
Yeah, great question. So the question is, if you're randomly sampling around the point theta, where does the line come from? So once we have our random samples, which are the differences from the original theta, we also need to find differences from the original u of theta, and then I'll talk about the method that we use for fitting the line between the two. But basically, we collect both of those data points and then use the method that we would use for regression. Like, I think this also came up in the policy, or no, the approximate value function chapter as well. Yes, but that's a great point. That is what we need to do next. Any other questions? Yes.
Is that sampling on the sphere that you just mentioned?
Yeah. So let's see. I'll draw a picture, and hopefully this helps. But if not, let me know. So we have some normal distribution. So we're sampling from some normal distribution, and we could have any mean mu here. And then we're using the samples from that